Good afternoon, everyone. My name is Francesco Petruccione. I'm the interim director of NITheCS, and I have the pleasure to introduce to you the last speaker in this mini school series on energy materials. The speaker today is Professor Chad Kruger. He's an associate professor of physics at the University of Pretoria, but he completed his PhD and a postdoctoral fellowship at the Free University in Amsterdam under the supervision of Professor Ring van Grombelle, if I remember correctly. Yeah, excellent. Yeah, and Chart is a passionate photosynthetic light harvesting complexes specialist, yeah? And I assume he will speak a little bit about that today. Chacha has also been very strongly engaged in the South African Young Academy of Sciences. He's also currently the chair of the South African Biophysics Initiative. And he's also, although he's so young, already a senior editor of Journal of Physical Chemistry Letters. So well done for that chart. That's quite an achievement. Yeah. So Chad, I don't know, you want to start sharing your screen? While you do that, I remind our participants to make use of the Q&A at the bottom of the screen or towards the end of the talk to raise your hand so that we can give you the right to ask your question in person. Chad, please, you're welcome to start.
Right, thank you very much, Francisco, for the kind introduction. And yes, it's a pleasure for me to give the last of the 4 lectures on this topic of energy materials, the mini school series that we've been run the past month. And I'm going to talk about biological, biomimetic, and organic renewable solar energy materials. So it is, in fact, a very big topic that I'm going to address today. And this hour that I have at my disposal will allow me to only scratch the surface of some aspects of this big topic. I'm going to touch on just some aspects of what the previous lectures have dealt about, but my main focus is going to be on light harvesting, which will add a new dimension to the topic of this mini school. Right, so this is the outline of this lecture. Basically 3 points that I'm going to address. The first is I would like to give a big picture of photosynthesis and use that as the basis of mimicry and inspiration. So in the second point, I'm going to look at a few different types of solar cells that have been inspired by photosynthesis or are making use of some principles of photosynthesis or are actually making use of photosystems themselves in a hybrid way. And in the last part of the lecture, I'm going to give 2 examples of bioinspiration from natural light harvesting complexes that can be used firstly to limit photodegradation, and secondly, a principle that can be used to enhance the performance of some types of solar cells. Right, so looking at natural photosynthesis, there's so much that we can learn from nature, and even in the context of energy technologies. If we just consider that photosynthetic organisms are in fact solar plants, and here the pun is intended, so they're really solar plants, and even more than just converting solar energy to fuels, which are doing at a massive scale, transforming 300 terawatts of solar energy into fuels. These fuels are living matter. They also, at the same time, remove carbon dioxide from the Earth's atmosphere. So they are also doing a very big amount of carbon sequestration. So in this way, photosynthetic organisms are in fact addressing 2 of mankind's big global problems through the oneness process. Okay, photosynthesis is this process that operates on an enormous scale. So per year, there's about 105 billion tons of biomass produced by photosynthesis. So this is equivalent to 2 great pyramids of Giza per hour, every hour. So this is really energy conversion at a massive scale. There's also a huge variety when it comes to photosynthesis. So the 50% of photosynthesis is produced on land. The other half is produced by marine photosynthetic organisms. And within these two categories, there's also an enormous variety. So that itself is also a very interesting topic to explore, because within this variety, all these organisms have the same goal: to convert solar energy into utilizable forms of energy. Okay, so let's look at this question of what is photosynthesis. Well, the name itself is very telling. If we just divide it into the two components, photo and synthesis, it means that photosynthesis literally means to put something together, synthesize something with the help of light. So to make it more specific in the context of biology, it's a synthesis of new chemical compounds or biological molecules under the influence of light. Okay, so broadly speaking, it's light energy that's captured and stored by the organism into a form of energy that can be used. And the photosynthetic process is usually written in this deceptively simple equation. Okay, so this equation is for oxygenic photosynthetic organisms, where oxygen is given off as a byproduct and water is used. There are also a lot of anoxygenic photosynthetic organisms that do not use water as the electron donor, but use some other molecules. Okay, what we have here in this equation on the left-hand side is carbon dioxide and water are combined with photons to produce carbon hydrates, biomass, and oxygen is given off as a byproduct. So I'm saying that this is a deceptively simple equation because this equation, in fact, captures about 170 chemical reactions. Okay, often it's said that in photosynthesis, light is converted into fuels. Well, I understand why it's said to be like that, because it's this energy conversion process, but obviously this is not correct because the fuels contain mass. They are mass, particles with mass, whereas light consists of photons, massless particles. So we cannot obviously just create matter out of nothing. And in this case, Einstein's famous equation of E equals mc squared is not applicable. So more correctly, we have to say that, well, carbon dioxide and water, the carbohydrates, are our cheap molecules, which are then combined by using the energy from light into fuels. Okay, and since we are dealing with cheap, inexpensive molecules, this is actually a very attractive aspect. Carbon dioxide and water are amongst the most abundant molecules in nature. So this is already a great source of inspiration that very abundant molecules can be used in order to form fuels and fuels for the purpose of mankind. Okay. However, the fuels that we are considering here is biomass. Okay, and the complete energy conversion efficiency is less than 1%. In fact, under normal conditions, it's much less than 1%. If the conditions are optimized, we can get close to 1% for plants. We can get up to 3, maybe a little bit more percent for certain types of algae. Okay, this is not a very efficient process overall, but the main question is, okay, are we interested in this type of fuel? Well, these are biofuels, and this is indeed one of the modern day sources of renewable energies. But isn't there a better fuel earlier in the photosynthetic process that can be used? For example, are there not perhaps free electrons that can be extracted from the photosynthetic process to allow direct electricity generation? Okay, so these are amongst some of the questions that I'm going to address in this lecture. Let's first briefly look at the photosynthetic process, a general overview to see where the main energy is lost. Okay, so here's a depiction of energy flow in the photosynthetic process. So photosynthetic organisms access only about 50% of the incident solar energy, if one considers the full solar spectrum and the part of that that is absorbed by the photosynthetic pigments. So we start off with about 50%, and then there are several loss processes until we end up with a lot less than 1% of the energy, initial energy, that's finally stored in the form of biomass. The biggest loss process is due to regulatory dissipation. Okay. And this is actually understandable because the plant's main purpose is not to generate biomass. And thankfully, it's also not the main purpose of our bodies. The main function of the plant or photosynthetic organism is to maintain cellular functions and to adapt to environmental stimuli. And this costs a lot of energy. So if we could stop the photosynthetic process sooner and before a massive amount of energy is lost, we would be able to have a much greater amount of energy conversion. Okay, but we're also interested in other forms of energy, not only the biomass. Okay, so let's have a brief look at the global picture of the photosynthetic process to see what other possible fuels could be extracted from the photosynthetic process. Right, so we must view photosynthesis as a process whereby the energy is stored in increasingly more stable forms. And for this to happen, the energy must be converted into different forms along the way. So we are starting off with a photon, a solar photon, which is absorbed by the photosynthetic pigments like chlorophylls, and this produces an excited state, which is a very unstable form of energy because it decays typically in a few nanoseconds. Now, within this time, before decay of the excited state, the energy must be converted into a more stable form. And this is done in the photosynthetic reaction centers. So here's a very, very simplified form of the photosystem 2 reaction center. And excited state in this reaction center is converted into an electron-hole pair. And to prevent recombination, the electron is transported to the other side of the membrane, creating an electron gradient. In other words, a potential difference. And this difference is now a much more stable form of energy than the original excited state. The electron is replenished by extracting another electron via intermediates from water. And in this process, by extracting electrons from water, the water molecule is split, and what remains are protons and oxygen. So for every 4 photons absorbed, 4 electrons are extracted, and what remains is from 2 water molecules, 4 electrons are extracted, and 4 protons are released, and 1 oxygen molecule. Okay, so we here have protons that accumulate on the inside of the membrane, and this results in a second transmembrane proton gradient, so a second potential difference, a second way in which the energy is temporarily stored. Right, so in principle, these electrons and protons that have been released can be extracted in principle, and I'm going to show you some examples about, of that a little bit later. Okay, let's now just complete the photosynthetic process to look at the next forms of energy, which the protons and the electrons are stored. Okay, so because for these photosynthetic organisms, the electrons and protons are not a very useful form of energy. Instead, they are used by molecular machinery to synthesize stable molecules. So the electrons are used to synthesize NADPH, okay? The protons are used by this remarkable enzyme called the proton pump, ATP synthase, to convert ADP to ATP. Right, so now NADPH and ATP are the next forms of energy, and they are much more stable forms than protons and neutrons, which are obviously highly reactive. Okay, so where's our energy now? The energy has now been stored in the form of chemical bonds, and this energy can be released by breaking these bonds. In fact, ATP is the universal currency of energy in biology. It releases energy in basically all biological cellular processes by when a phosphate group is released. So when it turns back from ATP into ADP, it releases a lot of energy. Right, so all these processes that I've described so far, they are called the light-dependent steps of photosynthesis. After these light-dependent steps, the light-independent steps can start by combining ATP, NADPH, and carbon dioxide in a so-called Calvin cycle. And the Calvin cycle one can view as like an assembly line, as a small factory. You start off with a certain molecule at the first enzyme called Rubisco, CO2 is attached, and that leads to a splitting of this molecule into two identical parts. And then these two molecules go on the so-called conveyor belt to the enzyme where ATP and NADPH interact with it, and it forms the so-called molecule G3P. One of these G3P molecules will then be extracted, and the other one will then go via enzyme 3, and it will be recycled in this Calvin cycle. So the G3P is now a more stable form of energy, a more stable molecule in which the energy is stored. And this G3P is often converted, well, it can be used just as it is, or it can be converted into sugar or starch or cellulose, which are the main forms of biomass. Okay, on the next slide, I have a more colorful version of the light-dependent processes. And here you can clearly see the electron transport chain where the electron is extracted from water. It goes, well, in photosystem 2, it's extracted from water. It is then transported inside the membrane through photosystem 1, and then it attaches with NADP plus together with another proton to form NADPH. And here is the proton. So actually there are 3 ways in which the proton gradient increases across the membrane. So firstly, protons are released from water. Secondly, by means of the electron transport chain, additional protons are transported through the membrane. And thirdly, to form NADPH, a proton is extracted on the outside of the membrane to NADP plus form NADPH. So this removes more protons on the outside, and additional protons are accumulated on the inside. Right, let's focus for a moment on the water splitting reaction, because there are a few very attractive aspects of this reaction. Firstly, only earth-abundant elements are being used. For example, the enzyme that is used here is a manganese cluster. Manganese is an abundant material. In contrast to all the mimicking enzymes for water splitting in which rare earth materials are used in order to get a high enough efficiency. Okay. Secondly, the efficiency of this process, even in the absence of rare earth materials, is extremely large. So it has a great thermodynamic efficiency in the sense that there's only a small overpotential in the process to oxidize water. And this is a feat that is unmatched by any human-engineered catalyst. And thirdly, the protons that are released can be combined to form hydrogen as a fuel, or even other fuels, methane or so. And this has inspired a great amount of research in the past 2 decades, in particular, to create artificial systems to mimic the natural photostatic water splitting reactions. So let's look at a few of these systems. And I'm going to start with a photoelectrolytic cell to tie in with the first lecture of the new school series. So what you see here is the basic structure of a photoelectrolytic cell, which mimics the water splitting in oxygenic photostatic systems. So it starts with the absorption of a photon by a light harvesting network, the same as in photostatic systems, which also contain extended light harvesting networks, often called antenna systems. And the purpose of this light harvesting network is to concentrate the excitations to a particular point, because solar energy is a dilute form of energy. So we need to concentrate the excitations. Right, so this light harvesting system is a photosynthetizer. And then, like in photosynthesis, the excited state produces an electron-hole pair, and the electron is replenished from water through a catalyst. And this releases protons. Well, this is basically where the strict mimicking part stops, because the free protons can't really be used as fuels. They must be converted into a usable fuel. And that's the purpose of the hydrogen evolution reaction, a reduction half reaction on the other side, where in this case, the protons are combined into hydrogen. Okay, let me show you two examples whereby this principle is used. The first example here is a dye-sensitized solar cell, where the dye is porphyrin, okay, and it's sensitizing titanium dioxide, which is a photoanode. Okay, so upon photoexcitation, this porphyrin is excited, okay, and it then transfers an electron to the conduction band of titanium dioxide, okay, and that means that we have a porphyrin radical cation, okay, which is a passive molecule. It interacts in this particular example with NITH, which is an electron donor. Okay, so this is going to donate an electron to this cation, and we get the NAD plus protons. Protons can then diffuse through the proton exchange membrane to the other side where hydrogenase is. Hydrogenase is an enzyme that can transform protons into hydrogen. Okay, so this then completes our process, two half reactions, and one can then get a complete electric circuit. Okay, so overall in this process, the incident photon energy is converted into hydrogen, which is now a useful form for human purposes. Okay, let me show you another example here on the right. Okay, so here we have biohybrid, a biophotoanode. Okay, so this part on the left is the biomimicking part. Okay, it's mimicking the so-called Z scheme of photosynthesis. And the Z scheme is the oxidation reduction potentials in photosynthesis, a very common scheme to look at these oxidation reduction potentials of all the different intermediate forms of the light-dependent steps. Okay, so photosystem 2 is used in this case, the full photosystem 2. Okay, it captures the light and then it transfers the electrons via a polymer through quantum dot to our photoanode, titanium dioxide. Okay, on the cathodic side is another enzyme which will then convert the free protons that are released from photosystem 2 into water. Okay, so in this way, there's a water-oxygen photobioelectrochemical cell that can be constructed. And the nice thing about this paper is that this was done at a very low potential. Okay, so they managed to get a very high open circuit voltage, well, very high for such a kind of system. Open circuit voltage was about 1 volt under normal sun illumination. Okay, so yeah, there are many attractive aspects about this system, but the main downside is that this redox polymer, which is a catalyst, it contains osmium. Okay, osmium is a very rare earth material. Okay, so this is not the ideal system if we want to go for inexpensive systems, but at least it's a nice example of a biophotoelectrochemical cell that is mimicking some aspects of photosynthesis. Okay, let's look at another system, the so-called biohybrid solar cell. Okay, so we call it a hybrid solar cell in a case where biological parts are combined together with normally semiconductor materials. And these biological parts are then the low-cost, environmentally friendly either biomolecules or whole photosystems. For example, in example here on the left, complete photosystems were used. So here you can see the light harvesting antenna that's capturing the light. It is then transporting the excitations to the reaction center where the electron-hole pair is generated. The electrons are then transported to the anode via an electron acceptor, while the electrons, while the holes are then filled, or the electrons are replenished in the reaction center by means of an electron donor, which extracts electrons from the cathode. Okay, and this way you again have the complete electric circuit. Okay, the example here on the right is a very recently published paper. It was published earlier this month. And this is another example of a dye-sensitized solar cell, where now instead of a dye, a single molecule, a full protein complex was used. Okay, so in principle, one can attach the full photosystems to the electron acceptor, like the titanium dioxide in this case, or in the case of this study, bacterial rhodopsin was used, which is very similar to the rhodopsin in the back of our eyes. This is just the version that many light-sensitive bacteria have. So they have a bacterial rhodopsin that can sense light. So this bacterial rhodopsin contains a retinol molecule that absorbs the light. It will change its configuration, and through a number of processes, it can then release an electron. This electron will then go via titanium dioxide to the photoanode. And then the electron in bacterial rhodopsin is then replenished by means of some other molecular system in this case. Okay, so there are many different versions of how to construct these biophotoelectrochemical cells and biohybrid solar cells and so on. Okay, yeah, let me show you another example of a biohybrid solar cell. In the previous example, this was the principle used here was a dye-sensitized solar cell, but we can also use the principle of organic solar cells. So the general architecture in this case consists of several layers. And here's an example of using photosystem 1, which is quite commonly used. And this photosystem 1 is attached to aluminium, which is the cathode on one side. On the other side is the photoactive layer, which is our bulk heterojunction solar cell. So this is our organic part. It normally consists of organic polymers that will then extract the electrons from photosystem 1 reaction center and then transport it to ITO, which in this case is the anode. Okay, so glass is just the protection layer in this system. Okay, so the principle is quite similar to all the previous cases that I've shown. Now, instead of using a complete photosystem, biomolecules can also be used. So this is an example where two biomolecules were used, lycopene, which is a carotenoid. It is actually the carotenoid that gives the color red to tomatoes. And then there are also two types of chlorophyll derivatives that were used. And these pigments were then blended in a form that's typical for organic solar cells. So you have these different phases or domains that form. In this case, the lycopene serves as the electron donor, and chlorophyll is the electron acceptor. Calcium here is the anodic interlayer, with aluminium being the anode, and molybdenum trioxide is the cathodic interlayer. And yeah, ITO is a cathode in this case. Okay, so many different designs with varying performances and so on. So it's a very interesting field to work in from the point of view of material science. Okay, so if we look at these biohybrid solar cells, they are still, I would say, in their infancy. So a lot of different designs are being explored because they are still relatively inefficient compared to conventional solar cells. In the case of pigment blends, well, the charge generation efficiency is not very high. And in the case of complete photosystems, these charges are extracted at relatively late stages of the photosynthetic process, with the result that the yield is also relatively low. But there have also been recent efforts where charges have been extracted much earlier during the photosynthetic process. And here are a few examples of that. So in the first study, which was published earlier this year in Nature, quite a remarkable study, it was showed how electrons can be extracted from either photosystem 2 or photosystem 1 immediately after charge generation. Okay, so you can see here after this so-called P star state, so the excited state of this special pair of chlorophylls in a reaction center, the charges could be extracted by means of an electron acceptor, an oxidizing agent. For example, DCBQ, which is dichlorobenzoquinone, or another very common electron acceptor is methylbihalogen. So that was used in the case of photosystem 2, directly after charge generation, within 10 to 30 picoseconds. So this is really on a very short time scale. And in photosystem 1, the same was done at an even faster time scale. So between 1 and 3 picoseconds after charge generation, a fraction of these electrons could be extracted without causing damage to the plant. So in other words, cyanobacteria in this case, just another type of oxygenic photosynthetic system. Okay, so a fraction of these electrons were extracted so that the rest of the electron transport chain could continue unaltered. Okay, so photosynthesis could continue in its normal way, and at the same time, electrons could be extracted. And once you have free electrons, just attach it to the electrodes and you can generate electricity. Okay, a few years earlier, a similar concept was used to extract electrons from photosystem 2, but that was done a little bit later. And that was then done from the plastoquinone, so a little bit later in this electron transport chain. But this was also a remarkable feat due to the fact that electrons could be extracted directly from the electron transport chain of either completely living organisms, like in this case, live cyanobacteria, or from the isolated photosystems. Here on the right is also a very interesting example where succulent plants were used, like cacti, and electrons were extracted directly from these live cacti. Okay, so it required minimal engineering requirements, and the authors managed to produce an electric current directly, well, actually by inserting the electrodes into the cacti. So this was, I think, quite a very nice idea. Okay, so what I've showed you so far are a few examples of what one could say is biomimicry. And how I would define biomimicry as opposed to bioinspiration is that biomimicry considers the general design. You are taking many design principles into account, like what we saw for the photoelectrochemical cells, mimicking the complete photocatalytic water splitting reaction of photosynthetic organisms. So that's taking the general design principle. Biohybrid solar cells can also be seen as a kind of biomimetic system. So in this case, the system is not only mimicked, emulated, it's also sort of emulated, but as part of that, the full photosynthetic system, or part of the photosynthetic system, like the photosystems or the biomolecules, the pigments, are used in this design. Okay, in contrast to that, I would define bioinspiration as a study where some individual design principles are used. So one would then observe nature in order to overcome some, in order to identify some specific problems that are being addressed by the biological system, and then use that design principle and reproduce it in our own technologies. So obviously there's a big overlap between these terms, but let's for this lecture categorize them into these two parts. So in the second half of the lecture, I'm going to focus more on bioinspiration, where I'm going to look at some individual design principles and specific principles for photosynthetic light harvesting complexes. Okay, so here's a list of design principles of photosynthetic light harvesting complexes, and I could actually spend a few hours go into detail about each of these design principles, because these are really marvelous systems. There's so much that one can learn from them. But for the purpose of this talk, I'm going to focus on only some aspects of these two design principles. So we'll look at the high pigment density, and we'll also look at protection from photo damage, and only one type of protection. Right, so let's consider this simplified Jablonski diagram, okay, where we start off with an excitation which promotes an electron from the ground state to the first or second excited state, in this case, the first electronically excited state. Okay, then there are a lot of competing processes, radiative processes. So we have fluorescence in this case. They can be non-radiative processes, generally called internal conversion. And then there's also intersystem crossing. So that happens due to spin orbit coupling when the electron spin is flipped. And there are three ways to compose a system of two electrons having a total spin state of 1. So this is why this is called a triplet state, so triplet degenerate state. So this triplet state has a relatively long lifetime. And during this time, if it does not decay directly to the ground state and there's oxygen around, well, this is a recipe for damage. Because of the long-living triplet state, there are two types of reactions that can form. The first type is electron transfer from the triplet state to the oxygen. And oxygen in its ground state is a triplet state due to two unpaired electrons in two different orbitals. Okay, so oxygen can readily receive an electron. It's a strong electron acceptor that can generate oxygen anionic states and different types of so-called reactive oxygen species, which are highly reactive molecules, and therefore they can react with a lot of different molecules, causing a lot of damage. Okay, the second type of reaction is energy transfer from the triplet state to oxygen, and that will promote an electron, well, actually excite oxygen to produce singlet oxygen. Okay, and singlet oxygen is also highly reactive, so it can also very easily donate an electron and form different types of reactive oxygen species. Right, so how do photosynthetic organisms cope with this? Okay, how do they prevent the formation of reactive oxygen species, so either singlet oxygen or different other types of radical states? Well, the key design principle that they have is that they are packed with carotenoids. So carotenoids typically look like this. They have a linear conjugated tail. So this consists of carbon-carbon bonds alternating between single and double bonds. So a long linear molecule like this, and then often they have some cyclic parts at the ends. Okay, so these carotenoids are great systems to interact with the reactive oxygen species, which I'm going to show you now. Let me first show you how these photosynthetic light harvesting complexes are packed with the carotenoids. Okay, so this is the main light harvesting complex of plants called LHC2. It consists of 3 proteins that are basically identical, and each protein binds a large number of pigments. Okay, so we have 14 chlorophylls and 4 carotenoids. So the chlorophyll-carotenoid ratio is 7:2. Not particularly high, but each chlorophyll is adjacent to a carotenoid. So as soon as it's excited and the triplet state is accessed, carotenoid can then act to either quench the triplet state or to interact with singlet oxygen. Okay, here are a few other examples. So in diatoms, one of the main forms of phytoplankton, the main light harvesting complex is called FCP, which stands for fucoxanthin chlorophyll AC protein. The carotenoid in this case is fucoxanthin, and its ratio with chlorophyll is much higher than in the case of plants. So here we have a chlorophyll-carotenoid ratio of 5:4. In the case of dinoflagellates, another photosynthetic system, the light harvesting complex PCP, which stands for pyridinine chlorophyll A protein. In this case, the carotenoid is pyridinine, And now the chlorophyll carotenoid ratio is 1:4. So an extremely high carotenoid content compared to the main light harvesting pigment, which is chlorophyll. In the case of purple bacteria, so this is a type of anoxygenic photosynthetic organism, the pigments and also the different protein subunits are organized in beautifully circular symmetry. And the ratio of bacterial chlorophylls, which are just a slight derivative of chlorophyll, the ratio between this and carotenoid is 3:1. So also a pretty high carotenoid ratio, or carotenoid content. Okay, so upon formation of a triplet state, okay, and this is a process that wants to be avoided. So sensitization of the chlorophyll by formation of singlet oxygen. So now if carotenoid is nearby, its triplet state has a property of being lower in energy than the singlet state of oxygen. So it can quench the singlet oxygen when it's nearby oxygen, or it can directly quench a triplet state. So then you have triplet energy transfer. So in other words, this is the reaction that we want to avoid. We want to avoid the formation of singlet oxygen, and carotenoids do it in two ways. So they can either interact directly with the triplet state by means of triplet energy transfer, then chlorophyll will relax down to the ground state, and this triplet carotenoid is not a dangerous or very reactive molecule, okay, because of the low energy of its triplet state. Or alternatively, the carotenoids can interact with singlet oxygen, deactivate it in order to form non-reactive triplet oxygen. Okay, so yeah, this principle has already been used to some extent in the literature, but very little. So in my opinion, a lot more efforts can be done, especially in the context of dye-sensitized solar cells, where dyes are these photosynthesizers, molecules that can undergo the same process as what I've explained here, and also organic solar cells, where the organic molecules also share the same properties. So once you have a triplet state there, it can interact with oxygen and be destructive to the solar cell. Okay, so this is one in which we can gain inspiration from photosynthetic systems by adding molecules like carotenoids that can quench triplet states of the photosensitizers or directly interact with the reactive oxygen species in order to deactivate them. Okay, let's look at the second design principle, and we'll look again at LHC2, the main light harvesting complex of plants. And now we are going to look at the very high pigment density. So if you consider that this light harvesting complex can be approximated by a disk with a diameter of 7 nanometers and a thickness of just over 4 nanometers. And it is packed with pigments. So it contains 54 pigments, 42 chlorophylls, 12 carotenoids, where these molecules are relatively big. So the ring of chlorophyll has a diameter of about 1 nanometer, and the length of carotenoids is more than 3 nanometers. So just imagine 54 of these pigments packed into a disk with these dimensions. Okay, so this gives rise to so-called molecular excitons. So just due to the close packing of all these molecules, there's a strong overlap of the electron clouds, okay, and the electronic excitations are then delocalized over all these strongly coupled pigments. Okay, so let's have a brief look at the mathematical description of that. So these molecular excitons normally form when in the case of chlorophylls, the center-to-center distance is less than 2 nanometers. Okay, so let's consider interacting molecules such as these two chlorophyll rings. And for uncharged molecules, this interaction can be approximated by a dipole-dipole interaction. So let's consider that these are our two molecules, molecule 1 and molecule 2. So they are the two dipoles that are interacting. Both have a ground state of epsilon naught, and the respective electronic excited states are epsilon 1 and epsilon 2 with an energy difference of delta epsilon 1, 2. Right, so we can now write the Hamiltonian for this whole system. Okay, so if you just consider the two fixed isolated molecules, the eigenstates are both governed by this, the Schrödinger equation. Okay, but we're interested in the combined system. So let's write the combined ground state wave functions. It's just a product of the individual wave functions. And the ground state energy now contains, in addition to the two individual Hamiltonians, also the interaction term. And this interaction term leads to a displacement of the ground state energy of the total system, which I'm going to show you in a while. Okay, the excited state wave function is now a linear combination of the two possibilities. So what we're doing here is to use the so-called Heitler-London approximation, where the eigenfunctions are linear combinations of the product of the molecular eigenfunctions. Okay, and we have our excited Dimer-Schrödinger equation. Okay, where we have this excited state wave function and our full Hamiltonian that must be used here. Okay, let's now firstly consider the case when the coupling between the dipoles is much less than their energy difference and also much less than interaction with the phonon environments. In other words, different vibrational modes. So in this case, the excitations remain localized on the individual molecules. Okay, that's the case for typical center-center distances greater than 3 nanometers. Okay, so the excited state wave function now, okay, if we start with the form on the previous slide, okay, in this case, we can set C1 and C2 both equal to 1. Okay, so we have these two terms, but you would say, wait a minute, the wave function now isn't normalized anymore. Well, that's great, because this is a classical phenomenon. Due to the weak interaction between these two dipoles, the first term here simply describes a situation where the first molecule is in the excited state and the second molecule not. Okay, and we can actually just simplify it by phi 1. That is exactly what the first term is. And the second term is just the other way around. Second molecule is in the excited state, first molecule is in the ground state. So this is basically just phi 2. So what we have now is simply the addition of the individual molecular wave functions. So this is simply a classical phenomenon. And in this case of weak intermolecular coupling, we are in a so-called Förster regime, where the excitations is localized on the individual molecules, and energy transfer proceeds by means of resonance energy transfer. So this is called Förster resonance energy transfer, or FRET. And typical picture of that is what we have here. In the case of weak intermolecular coupling, there is hopping of the excitation amongst the different molecules, or actually in the case of photosynthesis, between the different individual light harvesting systems. Okay, I've jumped a little bit ahead of myself. So this was the case for weak intermolecular coupling. Let's now look at strong intermolecular coupling, the other limit, where the interaction energy is much greater than the energy difference between the two interacting dipoles, and also much greater than their interaction with phonons. So in this case, the interaction energy gives rise to perturbations of the energy spectrum, and phi 1 and phi 2 are no longer the correct eigenstates anymore. Okay, so in this case, we must use this excited state wave function as the a linear combination of a product of the two individual molecular wave functions. Okay, so in other words, what we have now is that our excited state is delocalized over both molecules. Okay, and we are in this case not simply summing the individual eigenstates anymore, but the combined system's eigenstates must be used. Okay, so the new eigenstates are now required to be stationary solutions of the Dimer-Schrödinger equation. Okay, we can find the solutions in a normal way by taking the determinant, setting it to 0, and let's just simplify this discussion. We are going to look at identical molecules where we can simplify the notation into that. And now we have two solutions for the energy. Okay, so as you can see here, the two solutions give rise to splitting of the energy. So this is also called excitonic splitting or Davidoff splitting. And the molecular wave function is now delocalized over, or the exciton wave function is delocalized over both the individual molecules. Okay, so yeah, so something else to mention here is that V1 and 2, V2 and 1 are the resonance interaction terms. So they describe the oscillation of the excitation between phi 1 and phi 2. Okay, so this is a case again for the weak intermolecular coupling where one has the hopping phenomenon of energy transfer. In the case of strong intermolecular coupling, one has to take the linear combination between all the participating dipoles. And in the case of photosynthetic systems, the delocalization length, so the extent of this excitation is typically across 3 to 4 pigments. So it's spatially relatively big. Right, so this phenomenon of excitons, so specifically molecular or Frenkel excitons, to differentiate them from semiconductor excitons. So there are a lot of physiological benefits in the context of photosynthetic systems. I've listed here the five ones that I can identify. The first is it gives rise to enhanced light absorption. And to illustrate that, let's have a look at this LH2 light harvesting complex of purple bacteria. Okay, so due to all these strongly interacting chlorophyll, bacterial chlorophylls in this case, one gets a whole exciton manifold. So a lot of different energy levels, so a lot of different energy splitting that happens. And the distance, energetic distance between the lower exciton state and the highest exciton state is about 50 nanometers. So just by means of this excitonic interaction, one can create an energy ladder. And this obviously broadens the absorption cross-section. So photons of many different colors can be absorbed. And at the same time, it also enhances energy funneling. So to illustrate that, let's have a look at this cartoon. These are the different energies of our individual pigments as a function of their spatial position. And now if you just consider all the individual pigments separately and energy transfer amongst them, like in the first picture, it would require, in this case, 7 individual steps. Okay, so a relatively long process. Okay, if some of these pigments cluster together to form strong excitonically interacting states, one can picture it like this. Okay, in this case, only 3 steps are needed from the input to the output. So fewer steps are needed, which gives rise to enhanced energy funneling, so funneling from higher energy states to lower energy states, and also faster energy transfer. And not only because of fewer steps, there's faster energy transfer, but also if one would compare the underlying theoretical models, one can also predict that by using the correct model, there will be at least 10 times faster energy transfer if the correct picture, the excitonic coupling is taken into account. Okay, the fourth physiological benefit is that there's less trapping and energy loss in the light harvesting antennas. And this can be conceptually illustrated as follows. Let's say that this is our disordered energy landscape, and each of these potential wells, or actually free energy wells in this case, connected, well, it's a result of, for example, a defect in a semiconductor. So now if you have an excited state, it can get trapped in each of these wells as it tries to make its way from, say, the periphery to the state where the charge separation takes place. Okay, and in each of these traps, electron-hole combination can take place and the charge can be lost, or the energy can be lost. Okay, now if one considers these spatially delocalized excitations. One can conceptually see it as a spatially big excitation, which can smoothly roll over the disordered energy landscape and avoid the energy traps until it gets into the to the real place where it must be trapped in order for charge separation to take place. Okay, so how can we apply some of these principles to organic solar cells? And I'm going to end this lecture by showing one example of how this can be done. Let's have a look at, firstly, at the main principle, the working principle of organic solar cells. Okay, so we can divide it between 4 processes. The first process is exciton generation by absorbing a solar photon. Okay, and then in the case of a molecular exciton, the electron in a hole pair is on the same molecule. So it moves together from molecule to molecule. It only separates at an interface between a donor and an acceptor. So the second process is the diffusion of the exciton to a donor-acceptor interface. And it's only at the interface where the electron in the hole can be separated so that they dissociate. And then the individual charges can be transported to the cathodes where they will be collected. Right, the big problem of this scheme is the susceptibility to noise. Okay, and noise in this case causes energy traps like defects. Okay, and this tends to destroy the excitation. Okay, and it produces short diffusion lengths and strongly reduces the performance efficiency of the devices. So the traditional solution to overcome this problem is to make use of bulk heterojunction cells. And that is a case where the donors and acceptors are forming an interpenetrated network so that the exciton diffusion length is shorter than the the distance between 2 interfaces. So in other words, before the diffusion length means the average time before it will meet an energy trap. So in other words, before it can meet an energy trap, charge generation can happen at an interface. Okay, so that's the main purpose of this interpenetrating network. In reality, it looks more like this, okay, reminiscent of spaghetti bolognese, where the long polymers, the spaghetti, is the electron donors, and the small round molecules, the meatballs, they are the electron acceptors. Okay, so can charges efficiently move to the interfaces in this case? Actually, in reality, the domains often look more like this. So there are many places where an electron in a hole, after the charges are generated, can get stuck and not reach the anode or the cathode. Okay, so what is happening in this design, in fact, is that one problem is exchanged for another. Okay, so why don't we go back to nature and have a look at how nature has resolved this problem by looking at the light harvesting complexes and structure these domains such that, well, physically large excitons can form so that the defects, the energy traps, can be overcome. Okay, and this idea was applied in a paper that was published a few years ago by using ordered arrays of closely spaced molecules. Okay, so by means of this close spacing, physically big excitons can form, and now these excitonic states are not so susceptible to environmental noise anymore. So this issue of the limited exciton diffusion is not such a great problem anymore. Just to quote from the paper, the structural order that was now imposed in this system is paramount. It reduces energetic disorder, boosts charge and exciton mobilities, and assists exciton splitting. So just showing again one way of how we can get inspiration from natural systems in order to overcome some challenges or improve some aspects. Right, so to summarize this lecture, I've the 3 main points here. Firstly, the primary steps of photosynthesis are a valuable source of biomimicry and bioinspiration, specifically for dye-sensitized solar cells and organic solar cells. Secondly, if we look at the bioinspiration, two examples that I showed, carotenoids are excellent molecules to limit photooxidation. And secondly, large molecular excitons may offer an interesting way to enhance the performance of specifically, again, dye-sensitized solar cells and organic solar cells. So thank you very much for listening to this lecture, and I'd be very glad to receive questions. And if you are not listening to this live lecture, you're always welcome to contact me. Here's my email address, or you can also follow me on Twitter, or X as it's called these days. Thank you very much.
Thank you very much, Chad, for the very nice lecture and nice overview. Are there any questions from the participants? I don't see at the moment any raised hand, but please, you're most than welcome to raise your virtual hand, and I will give you the right to speak. Or maybe are there any comments from the other panelists, the other speakers in the mini school? Chat. Nobody seems to want to ask you anything. Maybe your talk was very convincing, it seems. Yeah.
Either that or completely not understandable, which I
No,
hope
no, that I don't think so, because I listened and I enjoyed it. Yeah. But maybe just to finish on a positive note, yeah. How do you think that this whole area will develop in the near future? Yeah, how close are we to achieve some serious breakthrough that coping nature allows us to save climate change?
Yeah, thank you. Obviously, this is a question that's probably on the mind of everyone. So I would say in this context, the breakthroughs probably happen, like in most areas of science, in small steps. So there have been significant breakthroughs in many respects in many of these systems. So there are so many different designs, and each of them have their pros and cons. Personally, I think we should not look at the biomimetic systems, because if you would put a biological system on top of your roof, it's not going to last very long. I'm much more in favor of bioinspiration. So using stable systems, which can be organic or inorganic systems, and be inspired by some design principles of natural systems in order to overcome some challenges that are being faced. So that was more the idea in the second half of the talk, where I wanted to look at some of these design principles. But yeah, the idea of, for example, extracting electrons directly from an intact photosystem, which I showed in 3 examples, I think that is a very attractive system. One could imagine, for example, growing grass on your roof, which is, for example, done in Norway, with the Scandinavian countries, and then imagine extracting some of those electrons to power your household devices. I think we are not very far from a technological application such as that. So
okay,
yeah, we have been learning very much, but I think there's also a lot
should
more.
we wait before we buy solar panels?
Well, I would encourage the use of more environmentally friendly systems. Obviously, one big concern is what to use with old panels, which are not biodegradable. So yeah, rather use solar panels with a lower efficiency, but that are more environmentally friendly. And I'm very much in favor of, for example, plastic solar cells. So these organic solar cells, although they have a lower efficiency, they are much more environmentally friendly. So that's definitely an avenue that we must pursue.
Okay, that's excellent. Excellent. Okay, wonderful. Chart, let me check again in the chat. There is nothing, nobody raised their hand, it seems. Then, it's my pleasant duty to thank you and your fellow panelists and speakers in this mini school. Kingsley, that we know very well, but also Professor McConnell and Professor Alene. Thank you very much to all of you for your time and for sharing your wisdom with the NITheCS community. Yeah? As usual, all the mini schools are recorded. So soon, give us a day or two, or even this last lecture, the previous 3, I think, already online on YouTube. The whole series will be there, and traditionally many more viewers watch it on YouTube than live. Yeah. So thank you very much for your effort, and I'm looking forward to stay in touch. Thank you very much. Thank you, Chad.
Yes.
Thank
Thank
you
you very much,
thank
Francisco, for the
and thank
opportunity,
you to
and
all the
also for my
all,
3 colleagues for the other lectures.
yeah. Thank you very much to the online participants for being with us the whole month. Yeah. Thank you. Thank you very much. All the best. Thank you.
Thank you.